चलो. Welcome. We are glad you are here. Myself, Gnanada Sunil Dhumne, and from BSc second year. My seminar topic is Bare Strength Theory. Contents: Bare Strength Theory. I will explain stability of cycloalkanes. Second, limitations. Introduction. This theory gives very nice interpretation about the specific behavior of chemical compounds associated with the bond angle strength. Adolf von Beers was honored with the Nobel Prize for a discovery of this strength theory in 1905. He explained the relative stability of the first few cycloalkanes. This theory, named after him, accounts for the ease of opening of cyclopropane and cyclobutane ring and also the stability of cyclopentane ring. Beers postulate that any deviation of the bond angle from the normal tetrahedral value would impose condition of a condition of internal strength on a ring. He also assumed that all cyclic rings were planar and thus calculated the angle through which each of the valency bond was deflected from the normal direction in the formation of various rings. This is called the angle strength, which determined the stability of ring. The cyclopropane, the three carbon atom occupies the corner of an equilateral triangle. Thus, cyclopropane carbon-carbon-carbon bond angle of the 60°, the impulse says that is the normal tetrahedral angle of 109 degree 28 minute between any two bond of the compression to 60 degrees, and that each of the bond involves is pulled in by 24 degree 44 minutes. The value 24 degree 44 minutes is represented with it represents the angle strength or the deviation through which each of the bond bends from the normal tetrahedral direction. In cyclobutane, the four carbon atom occupies the corner of the square. The cyclobutane has carbon-carbon-carbon bond angle of 90 degree. The deviation from the normal tetrahedral angle, which each bond shows, 9 degree 44 minutes. For example, Wittig reaction. In interpretation, the oxyphosphate, the normal angle bond, which opens very easily. In cyclopentane, the five carbon atoms lies at the corner of the regular pentagon. Thus, cyclopentane has carbon-carbon-carbon bond angle of 108. The deviation from the normal tetrahedral angle is 0.44 minutes. In cyclohexane, the six carbon atom occupy the six corner of the regular hexagon. The cyclohexane has carbon-carbon-carbon bond angle of 120 degree. The deviation from the normal tetrahedral angle, in which each bond shows minus 5 degrees 16 minutes. Similarly, in the case of cycloheptane, the deviation from the normal tetrahedral angle is minus 9 degree 33 minutes. In the case of cyclooctane, it comes out to be minus 12 degree 46 minutes. The result of the above calculation is summarized below. We can see this table. In this table, the cycloalkanes, and it shows the angle strength in it. Cyclopropane. In cyclopropane, the angle strength is plus 25 degree 44 minutes. In cyclobutane, the angle strength is plus 9 degree 44 minutes. In cyclopentane, the angle strength is plus 44 minutes. In cyclohexane, the angle strength is minus 5 degree 16 minutes. In cycloheptane, angle strength is minus 9 degree 33 minutes. In cyclooctane, the angle strength is 12 degree 46 minutes. Positive sign indicates the carbon bonds having the carbon bond have to the compression of satisfy the geometry, and the negative sign indicates that the carbon-carbon bond have widened to satisfy the geometry of the ring. In the example given below, the deviation from the normal tetrahedral angle is minimized in the case of cyclopropane. According to the Beer-Stern theory, cyclopropane ring should be expected to open up and the slightly provocation, and thus realizing the strength within it. Cyclopropane is known to undergo the ring opening reaction with Br2, HBr and H2 and else opening chain addition compound. We can see this diagram. The bonds are compressed with the angle strength of cyclopropane with the angle 24°44'. There are some limitations. First, the deviation from the normal tetrahedral angle in the case of cyclobutane is less than that in the case of cyclopropane. This signifies greater stability. Thus, an expectation cyclobutane undergoes ring opening reaction but only undergo more strict condition. The deviation from the only tetrahedral angle is minimum in the case of cyclopentane. This impulses the cyclopentane is undergoes listed strength and should be more stable. Then it is not surprising that cyclopentane does not undergoes ring opening reaction. The deviation from the normal tetrahedral angle in the case of cyclohexane is higher than that in the case of cyclopentane. The deviation increases continuously with increasing the number of the carbon atom in the ring. According to Beer-Stern theory, cyclohexane and the higher cycloalkanes should become increasingly unstable and hence it's more reactive. Contrary to this prediction, cyclohexane and the higher homologous are found to be quite stable. They do not undergo ring opening reaction. Instead, they resemble opening chain alkanes in reactivity, that is, they react by substitution. Thus, the Beer-Stern theory is satisfactorily according for the expectational reactivity of cyclopropane, cyclobutane and cyclopentane, but it is not valid for cyclohexane and the higher cycloalkanes. Thank you so much.